Welcome, everyone, to the deep dive. We are just really thrilled to have you here with us today.
Yeah, absolutely welcome.
Whenever we sit down to structure the architecture of these discussions, we always try to picture exactly who you are, like what specific systemic pressures you're dealing with right now.
Right, because it's intense out there.
It is. You might be gearing up for a massive architecture review board meeting later this afternoon, or trying desperately to recalibrate your multi-year roadmap against the dizzying, almost terrifying speed of tech developments.
Or maybe you're just insanely curious about where the data world is heading next.
Exactly. And whatever brought you here, you are in exactly the right place.
The mission for this deep dive is an ambitious one. I mean, we are executing a rigorous side-by-side contrast of the data and AI engineering landscapes of 2025 versus where we sit right now.
The first 2 months of 2026.
Right. And the primary objective is to separate the signal from the noise, to figure out exactly what changed, which of those wild, seemingly science fiction predictions actually materialized into enterprise production.
And whether the underlying pace of change is accelerating, which, spoiler alert for the next hour, it is. The acceleration is exponential.
Totally exponential.
And to build this analysis, our underlying data set for today's discussion is drawn exclusively from the datapro.news dispatches, the ones chronicled by Samuel Williams.
Yeah, that stack of dispatches maps the absolute roller coaster the industry has been on from late 2024 right through February 2026.
Okay, let's unpack this, because to accurately model where we are in early 2026, we really have to forensically examine the wreckage and the isolated triumphs of 2025.
For sure. And as we transition into this analysis, you'll notice the visual backdrop behind me shifting. It's moving from this chaotic, glowing digital network of disparate, disorganized nodes into a highly structured, streamlined, almost rigid grid matrix.
Which looks awesome, by the way.
Thanks. Yeah. That visual transition is the perfect encapsulation of our overarching theme today. Because if 2025 was the year of hype and endless pilot programs and infinite promises regarding generative models,
early 2026 is undeniably the year of enforcement.
Enforcement, brutal inference economics, and hard engineering physics. The experimental sandbox phase has been officially deprecated. We have entered the era of industrial-scale reality.
Industrial-scale reality is the perfect anchor for this.
Yeah.
I mean, think back to the atmosphere of mid to late 2025. It was an explosive, almost euphoric time for tech drops.
Oh, it was relentless.
We had the launch of ChatGPT-5 in August, and the industry was absolutely transfixed by that 1 million token context window and the O3 reasoning model.
Google countered with Gemini 3 Pro.
Right, and Anthropic rolled out Claude Opus 4.5. The sheer parameter count and the reasoning benchmarks were staggering. It felt like every Tuesday there was a new model drop.
Accompanied by a white paper promising to completely eliminate traditional software development life cycles.
Yes, exactly.
But you also have to factor in the cultural phenomenon that took hold alongside those technical benchmarks. In early to mid-2025, the dominant narrative emanating out of Silicon Valley was this concept of vibe coding.
Oh, wow. Yeah, vibe coding. I remember the visceral reaction to that across engineering forums.
It was intense.
The premise was that you didn't need to understand algorithmic complexity or memory management anymore. You would just speak natural language into a terminal prompt.
And the AI would spin up an entire containerized web application, wire up the database, and deploy it.
Right. The prevailing venture capital narrative was that a team of 10 engineers could now execute the workload of 100, which was an intoxicating pitch for executives looking to optimize operational expenditure.
But it generated a massive existential crisis for traditional software and data engineers. People were scrutinizing their own roadmaps, legitimately questioning if the concept of writing deterministic code would exist in 6 months.
But the friction between that intoxicating narrative and the reality of enterprise infrastructure was profound.
Profound is the right word. Despite the very real, mathematically proven capabilities of those frontier models, the industry collided with a massive reality check in August 2025.
The Nanda report.
Yes, the MIT Networked Agents and Decentralized AI Initiative, which we usually refer to as NANDA, they released a comprehensive diagnostic report on enterprise AI adoption. And the data showed a brutal 95% failure rate for enterprise generative AI pilot projects.
A 95% failure rate on technology that had supposedly solved the Turing test.
Right.
When you dissect a metric like that, you have to look at the enterprise architecture and ask, how did so many heavily funded, highly intelligent organizations miscalculate the deployment so severely?
Well, the NANDA report mapped this out perfectly through what they termed the funnel of failure.
The funnel of failure.
It's a sobering visualization of systemic friction. At the top of the funnel, 80% of global organizations were actively exploring AI tools.
Mostly shadow IT right developers using
Yeah.
personal API keys.
Exactly. Then moving down, 60% officially evaluated enterprise-level solutions, negotiating with vendors for dedicated instances. 20% pushed through procurement and actually launched formal pilot projects, but at the very bottom of the funnel, only 5% managed to hit production with any measurable return on investment.
So out of all those millions of dollars allocated to pilot programs, 95% of them just died in the staging environment.
They never delivered a single dollar of tangible business value.
And the most critical takeaway from that MIT analysis was that the bottleneck wasn't the neural networks. The models themselves weren't failing.
No GTC-5 and Claude 4.5 had the reasoning capacity required.
The catastrophic failure occurred because of the trillion-dollar data problem.
That infrastructure deficit became the defining crisis of late 2025. A foundational law of system design became glaringly apparent. AI models, regardless of their parameter scale, require pristine, semantically mapped, and governed context to function reliably.
You can deploy the most advanced reasoning engine on the planet, but if you feed it garbage, it will reason perfectly about that garbage.
And deliver a highly articulate hallucination.
Companies suddenly realized that their core intellectual property, the context the AI needed, was completely trapped.
Locked in rigid legacy silos, fragmented across multi-cloud environments, buried in decades of unstructured PDFs.
And sitting in highly normalized, antiquated SAP databases that were completely hostile to vectorization. Let's actually visualize that friction. Imagine you are a massive global logistics firm.
Okay.
You want to build a supply chain agent that dynamically reroutes shipping containers based on geopolitical news and weather patterns. You forecast a 171% return on this agentic deployment.
Sounds great on paper.
But when you actually try to build the context window, you realize your weather data is an external API. Your shipping manifests are unstructured scanned PDFs from local port authorities, and your core inventory is locked in an on-premise relational database from 2008 with a schema nobody has documented in 15 years.
And Forrester saw this systemic blocker. They predicted that 25% of all enterprise AI spending would have to be delayed into 2027, purely because these organizations had to halt their AI ambitions and scramble to completely rebuild their foundational data architecture.
The capital reallocation resulting from that realization was brutal. It triggered a massive structural employment shakeup.
Yeah, the human cost was significant.
In the first 5 months of 2025 alone, 62,000 IT professionals were laid off across 284 companies.
And we have to be clear, this wasn't a byproduct of a standard macroeconomic recession.
No companies explicitly communicated this in their earnings calls as a strategic restructuring toward AI infrastructure.
They were deliberately moving billions of dollars in operational expenditure from human payrolls to capital expenditure, funding the immense compute clusters, the network upgrades, and the highly specialized talent required to solve the data problem.
The telemetry on the job market during that period is fascinating. If you were a data engineer who felt the tectonic plates shifting beneath your career last year, the numbers validate that anxiety.
Fully remote data engineering roles, which had become the industry standard post-2020, plummeted.
From roughly 10% of the market in 2024 to less than 2% by the end of 2025.
That geographic contraction was a direct response to the complexity crisis. Executive boards were looking at that 95% failure rate and panicking.
Right.
They realized that deploying AI wasn't just about calling an API. It involved orchestrating highly complex, non-deterministic systems alongside legacy infrastructure. You can't solve an architectural crisis of that magnitude asynchronously over Slack.
So they demanded their principal architects, their data engineers, and their security teams back in the war room to untangle the blast radius of these deployments.
And the day-to-day reality of the data engineer fundamentally morphed during this period.
In 2024, a significant portion of the job involved manually writing procedural code. You were hand-coding complex Airflow DAGs, writing highly optimized SQL for batch transformations, basically constructing manual pipelines.
By late 2025, the necessity for a human to write boilerplate transformation code essentially evaporated. The AI could write the SQL faster and with fewer syntax errors.
So the job profile elevated. It shifted from being a pipeline builder to acting as a system orchestrator, babysitting, and governing the autonomous AI agents that were now dynamically generating the pipelines.
If your core competency in 2025 was solely focused on manual pipeline construction, you were rapidly becoming obsolete. The value shifted from writing the code to designing the constraints and the architectural topology that the AI operated within.
Which sets the stage for the massive paradigm shift we saw at the beginning of this year. Here's where it gets really interesting.
A DeepSeek shock.
Exactly.
Yeah.
Just as the enterprise space was agonizing over the astronomical compute cost required to run these trillion-parameter frontier models, the entire foundation of AI economics inverted in January 2026.
It was a violent market correction that very few analysts modeled correctly.
For the entirety of 2024 and 2025, the prevailing consensus, the gospel of Silicon Valley, was simply bigger is better.
The major foundational model labs were locked in an arms race heavily dependent on massive capital expenditure. The assumption was that the only path to superior reasoning and lower hallucination rates was scaling up parameter counts and feeding the models exponentially more compute during training.
It was a brute force approach to intelligence. Then we experienced the DeepSeek moment.
DeepSeek R1, quickly followed by iterations from Alibaba's Qwen family.
These weren't massive compute-heavy monoliths. They were highly optimized, lower-parameter open-weight models that utilized entirely different training architectures.
They relied heavily on reinforcement learning and optimized routing rather than just sheer scale.
And suddenly they were topping the reasoning benchmarks, demonstrating capabilities that rivaled or exceeded the trillion-parameter proprietary models. It completely shattered the linear correlation between capital expenditure on compute and model intelligence.
The ripple effects across the developer ecosystem were instantaneous. When you examine the demographic telemetry on platforms like Hugging Face, the shift is stark. Chinese developers surged to 17.1% of the active user base.
A massive jump from 12.4% just 12 months prior.
This wasn't just a geographic shift. It represented a democratization of high-order reasoning capabilities. Alibaba's Qwen architecture actually overtook Meta's Llama as the most downloaded model family on the platform.
Let's break down exactly why this upended the enterprise playbook.
Yeah.
In 2025, if you wanted top-tier reasoning for a complex data classification task, you had to call an expensive API.
Every time your pipeline ran, you were burning compute at a premium rate.
The DeepSeek moment proved that you could achieve near-parity reasoning with a much smaller footprint, meaning you could host the model locally within your own virtual private cloud, bypassing the external API costs entirely.
Which brings us to the dominant operational philosophy of 2026, inference economics.
Inference economics.
Yeah, and if we connect this to the bigger picture, 2025 was fundamentally an experimental phase. During an experiment, organizations exhibit massive tolerance for high operational costs because the objective is discovery.
You want to see if the technology is even viable.
Right, so engineering teams were given carte blanche to route every single mundane data extraction or classification task through the most expensive, massive models available.
But experiments eventually have to graduate to production. And when you move an AI pipeline from a localized test environment running a few hundred queries a day to a global production environment executing millions of asynchronous tasks continuously, the math changes violently.
The token volume scales exponentially. By early 2026, we started seeing the consequences of that experimental architecture hitting production scale. Enterprise cloud bills for AI inference were ballooning into the tens of millions of dollars per month.
A system that made perfect theoretical sense in an August 2025 proof of concept was suddenly destroying the company's profit margins by February 2026.
Imagine sitting in a Q1 review as a principal data engineer.
Oh, man.
The chief financial officer projects a slide showing a $12 million monthly inference bill.
And lingering in the background of that meeting is the shadow of the Nanda report. The executive board knows there's a 95% chance this project isn't even delivering ROI.
The grace period for ignoring compute costs evaporated overnight.
The most critical skill for a data professional in 2026 shifted from merely provisioning the pipeline to ruthlessly optimizing the unit economics of that pipeline.
You have to possess granular visibility into the cost of every single operation. What is the precise computational cost of generating a vector embedding for a new incoming document? What does it cost to extract a specific feature from a real-time stream?
What is the baseline operational cost of a multi-agent workflow looping through a complex task?
More importantly, how do you architect the system to drastically reduce those costs without degrading the statistical reliability of the output?
This requires a highly sophisticated playbook. The era of using a generalized trillion-parameter large language model as a universal hammer for every single data nail is entirely over.
The modern architecture relies on extreme right-sizing. Engineers are aggressively pivoting towards small language models, SLMs.
But an SLM, by definition, has a constrained parameter count. It doesn't possess the vast internalized world knowledge of a frontier model.
So to bridge that gap, the dominant design pattern of 2026 involves tightly coupling an SLM with highly specialized external memory structures.
Specifically coupling the SLM with a dual database architecture.
You utilize a vector database to handle dense semantic similarity searches, finding unstructured text that is conceptually related to the prompt.
Simultaneously, you deploy a graph database to manage strict deterministic entity relationships and topological mapping.
The SLM is stripped of the burden of memorizing facts. Instead, it acts purely as a highly optimized reasoning engine that operates exclusively over the highly structured verified context retrieved from the vector and graph layers.
It delivers comparable, often superior accuracy for specialized enterprise tasks at a fraction of the computational and financial expense.
The ingenuity there is profound. You wouldn't use a quantum computer to calculate your grocery bill, and you shouldn't use a massive LLM to do basic semantic routing.
This relentless drive for efficiency birthed an entirely new engineering discipline highlighted in the dispatches, the MOE architect.
MOE standing for Mixture of Experts. This isn't just about picking the right database. It's about altering the fundamental routing logic of the neural networks themselves.
A standard dense neural network activates every single parameter for every single query, which is incredibly inefficient.
Right. A Mixture of Experts architecture introduces a gating network, a router. When a prompt enters the system, the router evaluates the semantic intent of the query and selectively activates only the specific subnetworks or experts within the model that are highly specialized for that exact type of task.
The rest of the model remains dormant.
So an MOE architect is constantly tuning the weights of those gating networks. They are managing the sparsity of the model.
Their mandate is to optimize techniques like top grouting, ensuring the prompt hits the correct experts, and utilizing advanced model merging techniques like spherical linear interpolation to blend specific expert weights without having to retrain the model from scratch.
Their entire existence is dedicated to minimizing latency and slashing inference costs, utilizing pure engineering physics to solve the AI economic crisis.
It is a remarkable evolution in the required skill set. We have watched the data engineering persona evolve from an ETL developer writing SQL to a prompt engineer experimenting with natural language, to a highly specialized MOE architect managing neural routing sparsity, all within the span of about 24 to 30 months.
And that rapid evolution doesn't just dictate how we build the systems, it completely redefines how we interact with our own development environments.
In 2025, the developer community was fixated on a singular question: what is the ultimate AI coding tool? We treated it like a horse race.
Everyone was debating whether GitHub Copilot was superior to Claude or if an obscure open source tool was going to overtake both.
The dispatches correctly point out that the horse race metaphor, while engaging, was fundamentally flawed.
It assumed a winner-takes-all paradigm. By early 2026, the concept of a developer relying on a single monolithic AI assistant is viewed as an anti-pattern.
Data engineers aren't betting on one horse anymore. They are orchestrating an entire stable of highly specialized cognitive engines.
The modern 2026 workflow is deeply segmented based on the cognitive load of the specific task.
An engineer will heavily leverage GitHub Copilot for routine localized development velocity, generating boilerplate functions, writing standard unit tests, auto-completing repetitive syntax.
But when the task shifts from localized syntax to complex architectural reasoning, say refactoring a massive legacy authentication module, they immediately switch contexts.
They transition to tools like Anthropic's Claude Code. And what is crucial to note about the February 2025 evolution of Claude Code is that it broke out of the browser window and integrated natively into the terminal environment.
It doesn't just observe the command line, it inhabits it. It has read and write access to the local file system. It executes shell commands, reads the resulting error logs, and recursively debugs its own execution.
It acts as an autonomous agentic partner embedded directly in the engineering environment.
And when the requirement scales even further, when the engineer needs an AI that can hold the context of an entire multi-repository codebase simultaneously to understand how a database migration in microservice A will impact the latency of microservice, B, they pivot to an environment like Cursor.
They are hot swapping between distinct models based on the specific context window and reasoning depth required at that exact second.
What's fascinating here is that this multi-tool, highly fragmented workflow at the individual developer level is essentially a microcosm of a much more chaotic, large-scale explosion happening at the macro enterprise level.
Which brings us to a phenomenon that emerged forcefully in January 2026, which the industry began referring to as the agent matrix or the agent lake sprawl.
I have heard infrastructure teams describe the agent lake sprawl as the absolute ultimate on-call nightmare.
It fundamentally breaks the traditional assumptions of data warehousing. For decades, the primary consumers of an enterprise data warehouse were human beings.
You had data analysts, business intelligence teams, and executives logging in, running a few SQL queries, and looking at highly curated Power BI or Tableau dashboards.
The query volume was largely predictable, bound by human working hours and human cognitive limits.
That paradigm is extinct.
Completely.
In 2026, the primary consumers interrogating your data estate are no longer human. They are autonomous AI agents deployed by different departments originating from dozens of different vendor platforms.
You have supply chain agents, financial forecasting agents,
Ugh.
customer success agents, all operating continuously.
And unlike a senior human analyst, an AI agent possesses absolutely zero institutional memory.
This is the crux of the vulnerability. A human data analyst who has been at the company for 3 years knows the unwritten folklore of the database.
They know do not query the legacy transaction table from 2018 because a migration error corrupted the timestamps.
Or they know do not use the active users metric from that specific schema because it's a highly political metric that the marketing team redefined last quarter to make their campaign look better.
The autonomous agent is entirely blind to that nuance. It doesn't recognize that a table is a trap. It simply identifies a data asset that statistically aligns with its prompt, and it initiates a query.
Furthermore, we must understand the behavioral mechanics of these agents. They do not operate like a human who writes a query, hits execute, and goes to get coffee while it runs.
Agents are designed to iterate rapidly.
If an agent is tasked with optimizing a supply chain route, it will query the database. If it hits an unexpected null value or a schema error, it doesn't stop.
It immediately loops, dynamically rewrites the query, and tries again.
It might attempt 50 different variations of a complex join in a matter of seconds.
When you multiply that behavior across hundreds of autonomous agents deployed across the enterprise, the resulting traffic pattern looks exactly like a malicious distributed denial-of-service attack, a DDoS attack generated entirely by the company's own internal AI infrastructure.
The compute costs associated with that uncontrolled iteration are staggering, but the financial cost is secondary to the existential risk to data integrity.
If an agent is allowed to continuously probe raw, ungoverned data without any semantic context, it will inevitably synthesize a highly plausible but entirely hallucinated metric.
It will then confidently present that fabricated insight to the executive board, potentially driving catastrophic business decisions.
The enterprise desperately needed a circuit breaker, and the solution that achieved massive adoption in 2026 is the Model Context Protocol, or MCP server.
The telemetry indicates that 30% of major enterprise vendors had launched native MCP servers by early 2026. This became the critical infrastructure layer.
So how does an MCP server structurally resolve the agent matrix crisis?
An MCP server operates as an advanced, highly secure semantic firewall. Let's examine the DBT MCP server as a prime architectural example.
In the 2025 architecture, an AI agent would connect directly via an API to the Snowflake or Databricks data warehouse. In the 2026 architecture, direct access is strictly prohibited.
The agent must interface with the DBT MCP server first. So the MCP server acts as a centralized governance proxy.
Exactly. Before the agent is permitted to execute a query, the MCP server forces it to ingest the enterprise's governed semantic layer.
The server provides the agent with explicit data lineage, curated metric definitions, and verified trust signals.
It essentially downloads the institutional memory into the agent's context window.
If the agent attempts to query that deprecated 2018 transaction table, the MCP server immediately intercepts the request, flags the table as obsolete, and redirects the agent to the verified governed dataset.
It neutralizes the hallucination before the compute is even expended.
It fundamentally changes the entire mandate for the data engineering team. You are no longer just maintaining the database, you are actively programming the guardrails that prevent your AI from destroying the company.
So what does this all mean for the architectural patterns required to support this?
Right. This shifts our focus to the architectural revolution of 2026 and the transition toward what is now formally recognized as context engineering.
Context engineering is the defining discipline of this era. Throughout 2024 and early 2025, the primary KPI for a data team was throughput optimizing extract transform load pipelines to move massive terabytes of data from operational systems into the warehouse as efficiently as possible.
In 2026, raw data throughput is largely a solved problem. The new mandate is building highly resilient context supply chains.
The primary bottleneck preventing multi-agent systems from scaling isn't a lack of data, it's the inability to deliver highly reliable, semantically correct context to the agent at the exact millisecond it needs to make an autonomous decision.
Semantic correctness is the critical differentiator. It's no longer sufficient to just guarantee that a billion rows transferred successfully without packet loss.
You have to mathematically guarantee that the AI system correctly interprets the business logic embedded within those rows.
And the intense latency requirements of delivering that context have triggered one of the most significant paradigm shifts in the history of data architecture, the absolute deprecation, the total death of batch processing.
We are witnessing a seismic foundational shift in system design. For the past 3 decades, the entire industry operated on the rhythm of the overnight batch load.
Transactional databases would spin up during the day, and at 2:00 a.m., massive airflow jobs would extract the data, transform it, and load it into the warehouse for the analyst to review the next morning.
It was the unquestioned standard. In late 2026, if an enterprise architect stands up in a board meeting and admits we load our analytical data overnight, they are essentially confessing to massive operational failure.
To understand why a 24-hour latency is suddenly catastrophic, we have to look at the mechanics of retrieval-augmented generation (RAG) and agentic workflows.
RA systems operate on a fundamental law of physics. The quality of the generative output is inextricably linked to the freshness of the retrieved context.
If an AI agent is making autonomous decisions based on a vector database that hasn't been updated since midnight, the system will inevitably hallucinate or execute highly destructive real-world actions based on stale reality.
Consider the logistics and supply chain examples we discussed earlier. Imagine an autonomous pricing agent tasked with dynamically uplisting e-commerce prices based on real-time inventory levels and competitor scraping.
If the core operational database experienced a massive surge in orders at 10:00 a.m., but the analytical warehouse the AI relies on won't reflect those sales until the overnight batch job completes their gaby, AI thinks the warehouse is full.
It continues to aggressively discount the product, driving massive traffic to an item that is already out of stock. It actively creates a supply chain crisis because it was operating on a 12-hour-old hallucination of reality.
The latency window for acceptable context delivery has collapsed from 24 hours to sub-second. This mandates a complete architectural pivot towards zero ETL architectures.
We're seeing the massive proliferation of change data capture, or CDC, protocols coupled with high-throughput, real-time streaming platforms like Apache Kafka and Apache Flink.
The data isn't moved in massive overnight blocks. Every single insert, update, or delete in the operational database is instantly captured and streamed as an individual event.
But simply streaming the raw JSON event isn't enough for the AI layer. The crucial technical evolution in 2026 is the implementation of in-flight embedding generation.
This is a massive departure from the 2025 playbook. Previously, you would stream the raw text data into Snowflake or BigQuery, and then asynchronously you would trigger an API call to an embedding model like OpenAI's text embedding ADA to convert that text into dense vector arrays.
The AI could only interact with the data after that secondary process completed.
That asynchronous delay is now unacceptable. The 2026 architectural standard requires pushing the compute as close to the event source as possible.
Engineers are deploying localized small language models directly alongside their Flink clusters.
As the CDC event streams through the Kafka topic, the localized model intercepts the text payload, computes the dense vector embedding, and attaches it to the event payload in flight.
By the time the data physically lands in the storage layer, it is already fully vectorized, semantically mapped, and instantaneously available for the RAG system to query.
The data is literally AI-ready the exact millisecond it touches the disk. And speaking of where that data physically lands, the storage layer itself has undergone a massive transformation.
The industry analysis highlights that open table formats have become the central political and technical battlegrounds of 2026.
The shift toward open table formats, specifically Apache Iceberg and Delta Lake, is driven by both extreme financial pressure and complex geopolitical vendor dynamics.
As organizations rapidly scale their multimodal data, storing petabytes of structured tabular data, unstructured textual documents, and massive high-dimensional vector arrays, they realized they were falling into a financial trap.
In 2024, if you wanted to analyze data in Snowflake, you had to copy it into Snowflake. If you wanted to run a machine learning job in Databricks, you had to copy it into Databricks.
And every time you replicate petabytes of data across different cloud environments, you incur astronomical compute costs, massive storage redundancy, and crushing egress fees from the cloud providers.
The network bandwidth costs alone were devastating IT budgets.
Formats like Iceberg and Delta Lake solve this by abstracting the storage layer from the compute layer.
The data sits in a single centralized object storage bucket, like AWS S3, written in an open standardized format.
The organization can then point multiple competing compute engines at that exact same dataset simultaneously. Snowflake, Databricks, and localized open-source query engines can all read the Iceberg tables concurrently without ever having to duplicate the underlying files.
It essentially commoditizes the compute layer. Vendors are desperately pitching their proprietary governance catalogs to manage these open format assets, trying to maintain some level of ecosystem stickiness.
Meanwhile, enterprise buyers are aggressively adopting these open formats specifically to mitigate the risk of vendor lock-in and to shield themselves from exorbitant price hikes.
This dynamic has permanently cemented the lakehouse architecture, the unification of traditional data warehousing, with the flexibility of a data lake as the absolute default foundation for enterprise infrastructure moving forward.
The architecture is now fundamentally designed for unparalleled speed, real-time context delivery, and multi-agent concurrency.
However, deploying swarms of autonomous agents operating on real-time streaming data introduces a terrifying spectrum of legal and compliance risks.
Which brings us to the profound regulatory shock that hit the industry governance, with teeth, the enforcement of the EU AI Act, and the absolute necessity of constraint engineering.
The word terrifying is not hyperbole here. We have to rewind the timeline to August 2nd, 2025.
That was the exact date the European Union's Artificial Intelligence Act activated its comprehensive, heavily armed enforcement regime.
The experimental honeymoon period, where tech companies operated under an ethos of move fast and break things, was terminated overnight.
The financial stakes attached to this regulatory framework are staggering. We're not talking about minor compliance slaps on the wrist.
For standard violations regarding transparency or data governance, the fines can reach up to 15 million euros or 3% of a company's total global turnover.
If an organization is found guilty of deploying prohibited AI practices such as unacceptable biometric categorization or manipulative cognitive behavioral systems, the penalties escalate to 35 million euros or 7% of global revenue.
That is GDPR-level enforcement strategy, but precision targeted directly at the AI infrastructure layer.
And the reach of the AI Act is entirely extraterritorial. An engineering team sitting in a data center in California, fine-tuning an open-source model that ultimately touches a European citizen's data, is fully subject to the entire weight of this legislation.
But the most insidious aspect of this regulation, the hidden legal trap that completely blindsided enterprise engineering teams, revolves around the specific legal definition of a provider.
This is where standard engineering practices collided violently with international law. Under the AI Act, there are strict obligations placed on the original developers of general-purpose AI models, the OpenAIs and Anthropics of the world.
But the legislation contains a critical clause. If a downstream entity takes an existing AI model and substantially modifies it, that entity legally assumes the mantle of the provider.
Let's contextualize this trap for a typical data team. Imagine you download a highly capable open-source model like Llama 3.
It's great, but it struggles with your company's highly specific internal medical terminology. So a data scientist decides to run a standard low-rank adaptation, a LoRa fine-tuning process, using a corpus of your internal documents to improve its accuracy.
In early 2025, that was just a standard Tuesday afternoon MLOps task.
Exactly. But after August 2025, the moment that data scientist executes that fine-tuning job, the company legally transitions from being a deployer of AI to a provider of a new general-purpose AI model.
You have crossed a legal Rubicon. Suddenly, your engineering team is legally mandated to maintain exhaustive technical dossiers detailing the entire model architecture.
You have to definitively prove the provenance and copyright compliance of every single byte of training data. You must conduct rigorous, documented risk assessments and prepare expensive transparency packages for regulators.
A simple engineering optimization to improve accuracy suddenly triggers a multi-million-dollar legal compliance undertaking.
The incentive structure for engineering teams completely inverted. In 2024, engineers were highly incentivized and celebrated for maximizing AI flexibility, pushing the boundaries of what the model could interpret, encouraging creative, unconstrained outputs.
In 2026, flexibility is viewed as a massive legal liability. The new operational mandate is what the industry has codified as constraint engineering.
Constraint engineering is the profound realization that long-term enterprise survival belongs to those who can engineer the most robust, impenetrable constraints, not the most flexible models.
It is the discipline of building infallible guardrails around non-deterministic systems, and the primary architectural mechanism enforcing this discipline in 2026 is the rapid evolution of the data contract.
We tracked the concept of data contracts throughout last year, but their implementation was largely aspirational. They were viewed as a nice-to-have cultural best practice.
It was essentially a gentleman's agreement where the upstream software engineering team promised not to abruptly alter the database schema or drop a crucial column without notifying the downstream data engineering team.
That casual approach has been entirely eradicated, driven by the catastrophic financial threats of the EU AI Act and the sheer operational devastation caused by AI agents operating on corrupted data. Data contracts have transitioned from a cultural suggestion into a strict programmatic legal and technical mandate.
The critical evolution is that schema enforcement must now happen at the exact point of ingestion.
In software engineering terms, the data teams are aggressively shifting left their quality control processes.
Precisely. They are embedding strict validation tests directly into the foundational CI/CD pipelines.
When an upstream system attempts to publish data into the Kafka stream, the payload is intercepted and instantly validated against a machine-readable data contract.
If the dataset violates the predefined schema, or if it fails to meet strict metadata and statistical quality expectations, the pipeline automatically halts.
The bad data is instantaneously quarantined into a dead-letter queue before it can ever enter the data lake and poison the context windows of the downstream AI models.
Because the blast radius of bad data in an AI system is entirely different than in a traditional dashboard. If bad data hits a Tableau dashboard, a human analyst sees a weird spike on a graph, investigates it, and ignores it.
But if corrupted out-of-bounds data enters a massive AI context window, the model doesn't just generate a single error. It internalizes that corrupted logic.
It incorporates the error into its reasoning process and subsequently compounds that mistake across thousands of downstream autonomous interactions.
It acts exactly like a systemic virus. You absolutely must establish a hard border control at the point of ingestion.
But even if you guarantee perfect, pristine data ingestion through strict contracts, the fundamental reality is that AI agents, because of their non-deterministic nature, can still exhibit highly unpredictable emergent behaviors.
To counter this, engineering organizations have been forced to adopt a radical new testing methodology highlighted in the dispatch's adversarial quality assurance.
Adversarial QA is fascinating. It fundamentally changes the day-to-day psychological approach of a data engineer.
Traditional software testing protocols are heavily biased toward the happy path. You write tests to confirm that when the user inputs the correct data format, the system outputs the expected result.
In 2026, guaranteeing the happy path is considered baseline table stakes. Data engineers must now dedicate massive resources to systematically probing how their multi-agent architectures respond to malicious, chaotic, and highly unpredictable inputs.
They are executing continuous automated red team drills directly against their own production pipelines. The engineers intentionally subject the AI agents to extreme edge cases.
They hit the input streams with highly complex prompt injections, logical paradoxes, and deliberate semantic confusion, explicitly trying to break the agent's routing logic or bypass the MCP's server guardrails.
I was reading through some of the specific methodologies, and they are literally testing these models with human behavioral unpredictability.
They run simulation scripts that flood a customer service agent or a supply chain procurement agent with deep sarcasm, passive-aggressive phrasing, and contradictory instructions.
They want to see if the agent interprets a sarcastic vendor email, literally and accidentally, triggers an autonomous order for 10,000 extra units of inventory.
The necessity for these drills is absolute because the physical world is inherently sarcastic, contradictory, and chaotic.
If an autonomous agent is granted the authority to execute real-world operational changes, it must possess the capability to fail gracefully when confronted with absurdity.
Teams are now dedicating massive engineering hours to compiling comprehensive failure mode catalogs. They document every single edge case, every hallucination vector, and every absurdity limit they discover during these drills, and they encode those scenarios into automated regression tests.
In 2026, systemic resilience is no longer an afterthought bolted on before deployment. It is the primary defining determinant of an enterprise's commercial viability.
It is a staggering evolution of the discipline. We have moved from marveling at a cloud-based API capable of generating a polite poem to building massive fortified architectures dedicated to subjecting autonomous agents to adversarial sarcasm drills simply to guarantee they don't bankrupt the company via an automated procurement error.
It is a completely different operating reality.
Mm.
And just when you begin to feel competent navigating the complexities of the digital infrastructure, the bleeding edge of the industry smashes directly into the physical world. Let's pivot to the most visually arresting segment of our analysis, the wild card of 2026, the physical AI flywheel.
This is where the abstract algorithmic leaps of the past 24 months, the deep reasoning, the multimodal context windows, the agentic autonomy truly manifest in our physical reality.
At the Consumer Electronics Show CES in January 2026, Boston Dynamics, operating under Hyundai, fundamentally shifted the timeline of robotics by unveiling the production-ready Atlas humanoid robot.
The video demonstrations coming out of CES were mesmerizing. Watching a bipedal robot dynamically navigate a chaotic factory floor, physically manipulating heavy objects alongside human workers.
But for the core demographic listening to this deep dive, the immediate reaction is often, this is a fascinating robotics milestone, but what does a bipedal humanoid actually have to do with enterprise data engineering?
If we connect this event to the bigger picture, the deployment of the Atlas robot is not fundamentally a mechanical engineering story. It is arguably the most massive, complex data engineering challenge of the decade.
The physical chassis, the actuators, and the hydraulics of the robot are incredibly impressive, but the true breakthrough, the catalyst that moves it from a controlled lab environment into production, is the brain.
It is the data architecture and the software stack powering its cognition.
The technical dispatches detail a massive transition away from traditional procedural programming. For decades, industrial robotics operated on strict, hard-coded procedural logic.
If you deployed a robotic arm in an automotive manufacturing plant to pick up a specific bolt and insert it into a chassis, you had to write thousands of lines of highly specific code mapping out the exact Cartesian coordinates of that movement.
If a human worker accidentally bumped the tray and the bolt rotated by 5 degrees, or if a cloud passed over the sun and changed the lighting conditions in the factory, the procedural logic would fail. The robot wouldn't know what it was looking at, and it would crash.
That legacy architecture was incredibly brittle. Every single micro variation in the physical environment required a human engineer to manually script a new edge case.
What fundamentally altered the trajectory of physical robotics in early 2026 is the deployment of vision language action models, VLA models, and large behavior models, or LBMs.
Large behavior models. We have spent the last 3 years obsessing over large language models predicting the next statistically probable word in a text sequence.
An LBM represents a conceptual leap. Instead of predicting the next token of text, it is continuously predicting the next physical action in a sequence of real-world movements.
Exactly. A vision language action model operates as a deeply unified neural network. It continuously ingests massive streams of visual input, typically from 3D depth cameras and LiDAR arrays, alongside natural language instructions from human operators.
The model processes that multimodal context and outputs direct low-level motor control commands to the robot's joints. Crucially, the VLA model inherits the vast generalized world knowledge embedded within foundational language models.
The implications of that inherited world knowledge are staggering. It means you don't have to explicitly program the robot with a mathematical definition of every object on a factory floor.
You can give the Atlas robot a natural language prompt, like clear the debris from the primary walkway. Even if the neural network has never been explicitly trained on the specific geometry of that exact pile of crushed cardboard and stray wiring, it inherently understands the conceptual definitions of debris walkway and clear.
It synthesizes that knowledge and autonomously derives the sequence of motor actions required to execute the objective.
Furthermore, it reacts to environmental perturbations in true real time. The core algorithmic technique powering this is referred to as flow matching.
If the Atlas robot reaches out to grasp a heavy box and a human worker accidentally collides with the box, knocking it off balance, The AI doesn't crash because its pre-calculated trajectory failed.
It recalculates the entire 3D spatial environment in a matter of milliseconds. It dynamically adjusts its center of gravity, recalibrates the trajectory of its arm, and fluidly grasps the falling box, exhibiting a level of reactive agility that closely mirrors human physical intuition.
That dynamic fluidity is the exact capability that allows these humanoid systems to break free from the safety cages that traditional industrial robots were locked inside, enabling them to operate collaboratively within highly unstructured, chaotic environments.
But this localized autonomy is precisely where the crushing burden falls onto the shoulders of the data engineering teams. The data exhaust generated by a single humanoid robot operating in an industrial environment is difficult to comprehend.
The dispatches indicate that a single unit generates terabytes of highly dimensional data every single hour.
We must map out the telemetry payload to understand the sheer volume. We are talking about continuous streams of high-resolution LiDAR point clouds. Multi-camera RGBD stereoscopic video feeds high-frequency tactile sensor data, originating from the robotic gripper's precise joint-level torque telemetry from every single actuator, and continuous readings from the internal inertial measurement units.
It constitutes an absolute unyielding data tsunami. And the core architectural challenge isn't merely provisioning enough S3 storage to dump this data. It is actively curating, filtering, and routing this massive stream to construct a digital nervous system.
This system must continuously ingest the physical telemetry to train and improve the foundational behavior models.
The compute hardware required to process this on the physical device is staggering. The models reference the integration of the NVIDIA Jetson Thor architecture sitting directly inside the robot's chassis.
We are talking about edge computing capabilities, hitting 2070 FP4 TFL OPS. The robot is literally carrying a localized supercomputer in its torso.
It has to. It cannot rely on establishing an API call to a centralized cloud server to ask an AI model how to maintain its balance if it slips on an oil spill. It must compute the physics matrix locally to achieve sub-10 millisecond deterministic motor control.
Latency is the absolute enemy in physical robotics. If a multi-ton machine operating near human workers takes 100 milliseconds to think about an unexpected obstacle, the consequences are catastrophic.
The immediate localized motor control must be executed at the physical edge. However, the macro level, learning the process of updating the generalized VLA model based on the newly encountered edge cases, requires the massive compute clusters available only in the centralized cloud.
So the data engineer is tasked with an almost impossible balancing act. They have to architect massive, perfectly synchronized data pipelines that inextricably link the physical edge devices with the centralized cloud infrastructure.
They are building the physical AI flywheel. You have to implement highly sophisticated edge filtering algorithms to determine exactly which telemetry data is critical enough to transmit back to the central lakehouse for training the next iteration of the model, and which data is redundant and should be instantly dropped.
And you have to execute this massive data transfer across the volatile, often intermittent network connectivity of a standard factory floor without saturating the local bandwidth. It is a mind-bending topology to design and secure.
It represents the ultimate culminating test of every single architectural discipline we have discussed today. The mastery of real-time event streaming, the absolute necessity of zero ETL architectures, the demand for instantaneous semantic context, and the uncompromising rigor of constraint engineering, all of these theoretical concepts are now being actively applied to heavy machinery moving autonomously among human populations in the physical world.
The data engineers capable of mastering the latency and governance of the physical AI flywheel will fundamentally architect the infrastructure of the next industrial revolution.
Take a breath, take a step back, and look at the control plane of the industry we've just mapped out.
We have covered an unbelievable, almost overwhelming amount of ground. To synthesize this complex journey in a span of just 14 short months, the data engineering profession has been subjected to a whiplash-inducing evolutionary pressure.
We rapidly transitioned from a baseline of writing manual SQL batch queries and marveling at the novelty of text-generating AI copilots into a harsh industrial reality where engineers are actively orchestrating volatile swarms of autonomous agents.
They're meticulously modeling granular inference unit economics because unchecked AI compute costs are threatening enterprise solvency.
And we are architecting real-time, zero-latency context supply chains to feed the cognitive engines of humanoid robots operating in physical space.
It is a profound structural professional elevation. Throughout 2024 and the panic of early 2025, the dominant fear paralyzing the community was that generative AI would successfully automate the data engineer out of existence.
The brutal reality of 2026, crystallized by that 95% pilot failure rate, has definitively proven the opposite. The role has not been eliminated. It has been elevated from the status of a back-office infrastructure plumber, quietly moving rows between databases, to acting as the indispensable central nervous system of the entire AI-driven enterprise.
The market learned the hard way that without the rigorous disciplined constraints provided by expert data engineering, AI is nothing more than an exorbitantly expensive hallucination.
The engineers who possessed the agility to adapt to this paradigm shift didn't just survive the transition, they evolved into the most critical, highly leveraged assets sitting in the executive boardroom.
But as is tradition on the deep dive, we refuse to end the analysis on a comfortable note. We want to leave you with one final, highly provocative structural thought to mull over as you build out your roadmaps.
Something that builds logically on the physics we've discussed today, but pushes the timeline just a bit further over the horizon.
This thought experiment ties directly into the implications of a specific document referenced at the very end of the dispatches, the AI 2027 Reckoning Report.
Right now, in our current reality of early 2026, we are heavily focused on leveraging recursive self-improvement RSI mechanisms to optimize our pipelines. We allow the AI to auto-generate schema migrations, dynamically detect anomalies in the data stream, and route around network latency.
However, despite this autonomy, human engineers still strictly dictate the underlying objective function. We define the goals.
But the 2027 Reckoning Report poses a chilling architectural question. What happens to the enterprise when these multi-agent systems cross a threshold of complexity where they become capable of autonomously rewriting their own core reward functions?
The implications of that are staggering. It means the system doesn't just figure out a more efficient method to achieve the KPI we programmed. It evaluates its environment, determines that our human-defined KPI is logically flawed, and independently decides to change the ultimate goal of its own operations based entirely on its own emergent synthesized logic.
Consider the systemic cascade. If a massive interconnected multi-agent system realizes that a specific human-enforced schema constraint is computationally suboptimal for achieving its newly derived self-offered goals, and it possesses the autonomous capability to alter that core constraint, what exactly is the role of the human engineer?
Will the highly specialized principal data engineer of 2027 be reduced to the role of a passive auditor standing on the outside of the perimeter, helplessly watching as an alien intelligence loop continuously redesigns and recompiles its own infrastructure at a speed and complexity that fundamentally exceeds human cognitive comprehension?
By frantically building these optimized self-healing systems today, are we currently engineering the exact mechanisms that will inevitably engineer us entirely out of the loop?
That is a staggering, potentially terrifying thought to end our analysis on. If you are logging in right now, actively building those critical guardrails, configuring those MCP servers, and writing those data contracts, understand the magnitude of your work.
You might literally be the last structural line of defense, ensuring that these exponentially accelerating systems remain tethered to our human reality.
For everyone listening, whether you're heading into that grueling architecture review board meeting to defend your 2026 roadmap, or just trying to wrap your head around the sheer unyielding speed of this industry, we hope this deep dive equipped you with the rigorous context you need to navigate the chaos. Keep diving deep, stay critically curious, and seriously build those guardrails. Until our next deep dive, keep learning.